Hi everyone, it's Mrs. Woodruff. Today we're going to kind of turn things around. It's going to be kind of a sad day because instead of everything growing or money and population and such, we're going to see the opposite. Today is exponential decay. So you might remember from our first unit when we were doing sequences, we talked about exponential decay and we talked about the D words, and you're going to see right under Eeyore here. I thought it was an appropriate picture. You'll see, the decay, the death, the depreciation, down. Those are all the words that kind of tie into exponential decay. It's when a quantity decreases exponentially. It's going to decrease by the same percent in each unit of time. Now, our start amount obviously has to be greater than 0. Otherwise, if you multiplied by 0, or negative number wouldn't really make sense. But if you multiply by 0, this whole thing would get taken out. Today, our factor is going to be between 0 and 1. So it's less than 1. And that's what's going to clue us into things going down rather than increasing. We're still going to use our same exponential model where we have y equals a times b to the x. A is still going to be the initial amount of money, the initial population. It's going to be that start amount. And then the b is going to be a decay factor because today it's going to be in between 0 and 1. X is still going to be the number of time periods. We are going to do an example at the end where we're going to talk about a special kind of time period. And Y is going to be the resulting amount of money or population, after things go down. And at the bottom here, you can see an example of one. So to get the decay factor, again, we've talked about this. The decay factor is 100% minus the rate at which it decayed. So if you were dropping the population or your money was losing 15% each year, your decay factor is not 0.15. That's the amount you lost. The decay factor represents the amount you kept. So you take your 100%, your 1 minus the 0.15, and that would leave you with a decay factor of 0.85 or 85%. So if you lost 15%, you kept 85%. So there's sort of two ways to look at this decay factor, and you have to read the problem carefully. If they're talking about the percent you lost, you need to take that percent subtracted from the 100%. If they're telling you that it's the percent that remains, then you already have the decay factor. So here's an example of how the graphs look. You're going to remember that we've been talking about exponential growth, and right now it's in the news pretty heavily about this idea that all of a sudden an exponential growth will kind of take off. And if you notice over here, the exponential decay is kind of doing the opposite, where it's dropping rapidly and then kind of levels off. Neither one of these functions are going to cross this x-axis. They're never going to become equal to 0, but they're going to approach it and get closer and closer. So exponential growth is when the y value increases because of repeated multiplication by a number greater than 1, and decay is going to decrease due to repeated multiplication, but the number is between 0 and 1, and that's why it's dropping. So here's an example, one like we actually would have done at the beginning of the year. A business earned $85,000 in 1990. Then its earnings decreased by 2% each year for 10 years. Write an exponential decay model for the earnings. So here is our general form. We know that A is our start amount, and the value started at 85,000. It dropped by 2%. That means what percent was left? Well, 100 minus 2 would be 98% was left. So your decay factor is 0.98. Number one mistake would be to put a 0.02 in there, and then you're saying that only 2% was left. X is going to be the 10 years, the number of years. In this case, it'll be 10. And Y is going to be the value, or rather the earnings in dollars after that set number of years. So I'm going to write my general equation, but when I do it, I'm going to define my variables. X is going to represent the number of years. and y is going to be the earnings in dollars. I started with 85,000. My decay factor is 0.98. Unfortunately, my earnings are going down, and I'm going to put the general form here with the X up there. And now I can look for any number of years. What's going to happen in 10 years? What's going to happen in 20? I can just replace and substitute a different number in for X to see. In this case, I'm going to substitute the 10. And then I head over to the calculator and I take 85,000 times 0.98 raised to the 10th, not times 10, but exponential, raise it to the 10th power. And you should see that the business is $69,451.19. And again, we're going to always round to money, which would be the second decimal place. Notice, how much the value of that business has dropped in 10 years. In 2011, you purchased a parcel of land for $8,000, and the value of the land depreciates by 4% every year. What will the approximate value of the land have been in 2018? So here again is a D word. Depreciate means going down. So this is a decay problem. So now careful, the 4% isn't what's left. You're losing 4%. So you take 100 and subtract the 4%, 96% got left. So your B is going to be 0.96. Your A is the original amount, which is 8,000. And then we've got to see how many years are in between here, but let's start with defining our variables. So X is going to be the number of years, Y is going to be the value of land in dollars. Our general equation, including our Y and our X that we just defined, start amount, decay factor, and there's our X, which will be the number of years. Y is the value of land in dollars, and that's what you should always put when you're doing an exponential either growth or decay. You define your variables and write the general equation before you substitute in the years. And in this case, if you look from 2011 to 2018 is going to be 7 years. Just reminding you, where did the 0.96 come from? That was the 1 minus that 4%. Is where we got the decay factor. And I head to my calculator and I take 8,000 times 0.96 raised to the 7th, and I end up with about $6,011.58. So my value has dropped. This is kind of what happened about 12 years ago or so, when a lot of people, all of a sudden, their homes that they had bought, the value dropped, and they had a loan where they still had to pay a high value for the house, and yet the house was actually worth less than the loan they had to pay. It was kind of called a recession. You might have heard of that. Okay, so here is our new type of problem today. We have not seen this type of decay problem. It's called a half-life, and it is very important in the land of chemistry and science, and just when we're talking about how things decay in our landfills, or if you're talking about medicines in the body. Those are all kind of examples where our new problem is going to be used, and it's called a half-life. So the half-life of a substance is the length of time it takes for 50% of the substance to decay away. So again, it could be a radioactive substance, it could be a medicine in the body, something like that. So with radioactive substances, the half-life is the time for half of the radioactive element to decay to a different or another element. To treat some forms of cancer, for instance, doctors use radioactive iodine. The half-life of iodine/131 is 8 days. So this is the name of a radioactive material right here. So every 8 days, half of it would disappear, half of it would change. So if a patient receives 12, there's the initial amount, and this is called millicuries. It's a measure of radiation treatment. It's the unit, it's the grams, the inches, the feet. Millicuries is just another type of unit, in this case for measuring radiation. So if the patient gets 12 millicuries, we want to know how much of that iodine 131 would be left in the patient 16 days later. Okay. So we're going to make an equation to model this. It is an exponential decay. This time we're going to let x be the number of half-lives, and y is going to be the number of millicuries of the iodine-131 that's remaining. So how much of that is remaining in the patient? So we're going to let y, the amount of iodine, equal the start amount, which was 12. And the cool thing about half-life is your decay factor is always 0.5. Half means 50%. So in a half-life problem, this is always going to be 0.5 raised to the x. So here's our general form along with our definition of variables. In this particular case, we want to know 16 days. That does not make x 16. Because a half-life is 8 days. So 8 days is sort of like 1 unit of time. So 16 would be 2 half-lives. 16 divided by 8 would give us 2 half-lives. So we would now pick up our calculator, take 12 times 0.5, raise it to the second power, and you would see that there would be 3 millicuries left in the patient after 16 days. So let's do a couple more of these new types of problems. I'm going to read the first one, and then I'm going to ask you to pause the video and try it yourself. And we'll do the same thing with the second one when you come back. So if you start with a 50 millicurie sample of iodine-131, how much iodine-131 is left after part A, 1 half-life, and after 2 half-lives? So we're going to define our variables. We're going to write an equation, and then we're going to try it for 1 and 2 half-lives. So why don't you pause the video and see if you can do that part yourself, and we'll be right back. Okay, everybody, let's see how you did. So x, again, would be the number of half-lives, and y is going to be the amount of millicuries of iodine-131 remaining. The equation is going to be y equals your start amount, which in this case was 50, times the 0.5 for your decay factor raised to the x. So they made it easy on you here because they told you what the x was. They said it was going to be 1 half-life. So you're just going to take 50 times 0.5. Don't really need to raise it to the 1 because that is 0.5. And you should see there's 25 millicuries left, which makes sense. 1 half-life would cut that in half. So it goes from 50 to 25. Now after 2 half-lives, right, it would be 50 times 0.5 raised to the second power, and you're going to see it's 12.5 millicuries. And so you can kind of see that every half-life is taking away half of the substance and half of it remains. Okay, let's read number 2. Cesium-137 has a half-life of 30 years. Suppose a lab stored a 60 millicurie sample back in 1973. How much of the sample would be left in 2003 and 2063? How about if you pause the video and see if you can set that one up? Okay, let's see how you did. So we're going to define our variables first. X is going to be the number of half-lives, and Y is going to be the amount of millicuries of cesium-137 remaining in the lab. Our equation, we're going to start with our 60 millicuries. Half of it is going to disappear. That's the 0.5 raised to the number of half-lives. Okay, so this time we've got to be careful. We've got to figure out how many half-lives would be 2003 and how many half-lives would be 2063. So you're not just looking at the number of years. You have to realize that every 30 years is a half-life. So from 1973 to 2003 would be 1 half-life. It's 30 years. So 60 times 0.5, you would end up with 30 millicuries. Now go back to 73 and go to 63, and that would be 3 half-lives, and that's where I was just saying the 90 because it's 90 years. So 30 3 times, and that's where the 3 comes from. 60 times 0.5 raised to the third, and there would be 7.5 millicuries left remaining after those 90 years. You'll often hear discussion about the effects of like radiation and stuff in the atmosphere, and you can see kind of what happens here, that some of it gets, remains. All right, the last one is just going to couple a couple of ideas. We're going to kind of bring some ideas back from our unit 3, which was our function unit, domain and range and function notation. I just want to kind of see if we can't bring that to the forefront of our brains. So the radioactive decay of a 1,000-gram sample of iodine 108 is modeled by this exponential function. So you can see there's the start amount. You can see there's the 0.5, 50% is going to be lost and 50% is going to remain. T is going to be the number of half-lives, and F of T is going to be the grams of iodine 108 remaining. So let's just talk about what possible numbers could be in the domain, which means what numbers could T take on, like up here. So if you think about it, the smallest number that you could have for the number of half-lives would be 0. And the largest number is, we don't know. So in our interval notation, you're going to remember this. So I've got a bracket over here because 0 could be included and could be used. And it's going to go up to infinity. It could be 12 half-lives, 14 half-lives, who knows. And we have a parenthesis over there because you can't have a bracket. We talked about that with an infinity symbol. Now, what could come out? That's what can go in for T. Now, what could possibly come out? So this is a decay function. The biggest number that's going to exist is your start amount. It's going to get smaller from there. So 1,000 is going to be our biggest number inclusively. This is going to go down. Think about the graph. It's going to go down and down and down and down. And it's going to get closer and closer and closer to 0, but never quite reach it. So our range is going to be 0, not inclusively, and the biggest would be 1,000 with the bracket. So that's the only numbers that could come out of the function. These are the only numbers that could go in. What is f of 3 and what does it represent? So we're going to put a 3 in for the t and do the math. And when we do that, we're going to get 125 grams. What does this mean? It means that after 3 half-lives, there is 125 grams of the iodine 108 left. How about this next one? What's f of 1 minus f of 4? So I'm going to put 1 in for t, do the math. I'm going to put 4 in for t, do the math, and I'm subtracting them, and this is the number that I get. So from the first half-life minus the fourth half-life, I have 437.5 grams. And what does that mean? That between 1 and 4 half-lives, the 437.5 grams of the iodine 108 have gone away. So there's just kind of a connection to some of the stuff we did in our Unit 3, bringing back the idea of domain and range and interval notation, function notation, and sort of describing kind of what's happening here. Each time I input a number into this exponential half-life decay, it's telling me how much has gone away and also how much remains. That's kind of our new problem for today. So that's it, guys. I hope you understand kind of what's going on with exponential decay. I will post the filled-in notes pages for you, and there will be a worksheet to give some practice on. Hope you have a great day. Bye, everyone.